Okay, so we've got Daniel Haxton who's going to talk about dissociative electron attachment cross sections.
This is probably not on. This is not on, right? This is not on. Maybe it is on.
No, it's not online, so there is a problem. Yeah,
Is it on? All right, I'll continue. So I will be talking about calculation of dissociative electron attachment cross sections. There is one such cross section that I will be explaining later. So dissociative electron attachment is the basic process by which you have a molecule AB attaches to electron, and that breaks apart into A minus plus B. Those could represent many atoms, certainly. DEA can be damaging to biological and technological things because it produces radicals and anions. So we don't want to hurt any biological things. One thing that's motivated our research into dissociative electron attachment, this slide has been up, you've seen this many times, but it's been radiation damage to DNA. If you do have high energy ionizing radiation, it's an organism, it can, or anything, it creates a shower of secondary electrons, and these slower energy secondary electrons can do damage, in particular to DNA, as demonstrated by Sanch et al. In 2000. But as of late, there has been a lot of study of DAA onto biologically relevant molecules. So it's important to realize that DEA is a two-step process. Okay, so the first step, or can be thought of as a two-step process, the first step is electron attachment. You create a metastable anion, and then that metastable anion dissociates. And importantly, the reverse of process 1 competes with process 2. And that's going to be like the main take-home message of my talk as far as calculating uncertainties. It's that competition with the reverse process going back to the electron in neutral. So the schematic there that I've drawn is in terms of potential energy services. There can be an initial attachment step to your metastable state that lies above. Now that can dissociate, and if it makes it to the anion, the bound anion products here, A plus B minus, then you have dissociative electron attachment. But the electron can detach before it makes it out there, in which case we don't. And what that leads to is vibrational excitation. So basically, if you have the attachment process, if you create AB minus, there are really two ways that can go, is vibrational excitation or dissociative electron attachment. So that branching ratio is a big issue here. Now there are other non-resonant processes, but these don't compete. These aren't competing channels for dissociative electron attachment. And these don't proceed via a metastable intermediate. So a little more about that right here. In general, there are often, there can be simple systems in which you either have vibrational excitation or dissociative attachment. Vibrational excitation, you might have a potential energy curve that's actually bound, so you don't have a dissociative channel. So no matter what happens, the metastable state can't go anywhere and will eventually decay back to A plus B. You might have a very long-lived state, in which case, once you attach, you're definitely going to go to dissociative attachment. But in general, you do need to account for the competition between these two processes. You need to account for the decay of the metastable state. Now, when we talk about these things in terms of the intrinsic width of the state, that's the inverse of the lifetime. And the pictures I've drawn we viewed as potential energy services with a negative imaginary part. So that negative imaginary part is what, within the theory that we use, is responsible for the reverse process. So, just nailing that home, 2 steps, attachment and dissociation. The big picture is calculating that first step, attachment, is relatively easy. That's the relatively easy part. If the lifetime is small, if the lifetime is large, the width is small, you're going to have a small probability to attach, but once you do attach, you will not detach. So if the lifetime is long, really all you need to do to calculate the total cross-section is to calculate the attachment probability, because all of that will go to dissociative electron attachment. However, calculating that survival probability is much harder, and with a polyatomic molecule, one might need to actually perform polyatomic nuclear calculation to get that right. Now you can get a feeling for how that is going to lead to massive uncertainty as follows. The simplest equation I wanted to write down was that. I'm not advocating a parameterization like that, but the attachment probability is proportional to the width, and then if you say, okay, the molecule will take a certain time to dissociate until bound, and its width is always the same until then, well then you have the exponential term, which is the survival probability. Obviously I should be dividing that by h bar. So in other words, let's say for sake of argument, I know the width. I say, oh, maybe it takes 10 seconds to dissociate. Okay, well, with that, we get a survival probability of 90%. Well, if it takes twice as long, or sorry, a survival probability of 10%. If it takes twice as long, that survival probability is going to be 1%. So you have that exponential is a problem. Small relative errors can lead to large errors in the survival probability. Okay, so I would advocate the general perspective is that whatever I'm reporting, even if it is just theory, the uncertainty in my theoretical result has got to be a function of the ratio of vibrational excitation to dissociative electron attachment. Someone comes to me and says, I've calculated the dissociative electron attachment cross-section for this process to 1%. I say, what's the survival probability? He says, oh, it's about 0.1%. I say, there's no way you've done that. It's not possible for you to have done that. So, a priori, if I know that vibrational excitation is vastly dominant, I know that essentially I have very, very little chance of calculating this accurately, at least presently. So if you know this ratio, if you know the ratio of vibrational excitation to dissociative attachment, that'll tell you about the uncertainty. Also, the isotope effect will affect the survival probability. So if you have a large isotope effect, that would also, regardless of if you calculated that or measured it, if you have a reasonable certainty in a large isotope effect, then you have to say that your uncertainty in dissociative attachment cross-section is large. So here's an example of water. This is to hammer home the point that these systems are polyatomic and they lead to many different channels. So for instance, here we have, so you see here we have 3 peaks. Well, you clearly see 3 peaks here. There are a total of 3 peaks, and those are 3 electronic states. Okay, and then we have the 3 final dissociation channels. You see the magnitude of the cross-sections are very different. You go from 1500 down to 6. And I'll show you our calculated results here, but in general we can nail that top peak, the big one, very, very closely to within percents. And we don't even have a theory for that. So the uncertainty here is large. We have not attempted to calculate OH minus. We have attempted to calculate the others. Okay, so our motivation, I'll just skip through this, is in terms of angular distributions. It's not pertinent to this conference, but just for background. If we measure the angular distributions and do some calculations, we can infer things like, oh, when electron attaches to water via this state, it then scissors backwards and breaks up into 3 body. So that's our motivation. We also have some stuff on acetylene. So we use the complex cone method to calculate the resonance lifetime. And won't belabor the point. You'll be hearing from Jimena about the R-matrix method, and you've already heard about how a lot of these things are set up. It was developed, credit to Tom Rossini, Anna Rell, Ren Langsfeld, and Bill Curdy, developed over many years, and the basic premise is that we have continuum wave functions, explicit continuum wave functions, and quantum chemistry with Gaussian orbitals. And similar representation of the wave function as you've seen before, and you may see again, in terms of close coupling expansion, that's the first and second terms, target states phi alpha times other stuff, plus additional terms required for completeness. Now, and I'll just mention that we do have an option now of not using that third term and not over-correlating the target. That's a minor issue. Now, the code at present is limited. It's not a parallel code. We can only do small systems, several, a handful of atoms precisely. And if we want to do a correlated calculation, you definitely can't get big. Energies can't be too high, and it's archaic Fortran 77. It's very difficult to work with. We are planning a new Bill, Tom, and Bob here are planning a new implementation. Overall, I would say that the future looks promising for calculating, the present and future is promising for calculating total widths, the lifetimes of states. The path, you've already heard about more sophisticated parallel codes for calculating scattering, and hopefully we'll be able to push the cone suite to bigger molecules. But also, there's much effort on doing the problem directly using quantum chemistry. In other words, directly calculating the resonance lifetime just from an eigenfunction, not doing a scattering calculation. So really, it's calculating DA cross-section, just to hammer it home. It's not the attachment probability, it's the survival probability that's the problem. Okay, so to give you a little idea on that, these are some results on CO2. So there are 3 electronic states that you can see in the top figure that are responsible for DEA. Some people think there are others also. It's a complicated system. Now here I've shown, on the left I have the total cross-section, 1.5 times 10 to the minus 15. Here's the vibrational excitation, 1.5 times 10 to the minus 16. And DEA is 10 to the minus 19. So I'll give anybody $1 million if they can calculate the cross-section within 10%. And to help explain why this comes about in CO2, here I've plotted the lifetime, essentially, of the state as a function of geometry, of one of the resonance states of CO2 as a function of geometry. And now I should have plotted the lifetime. But sorry, this is the imaginary component of the energy. So when that is large, the lifetime is small. So this is a function of bend and stretch. Molecule starts at 0 bend angle there. You see there's not a node, but a strong minimum in the lifetime there. And as soon as you start bending the molecule, this state, the width gets huge. So here, this is a good example, CO2 certainly is a very good example of the dynamics being determined probably arguably more by the width than the real part of the surface. I think potential surface will push things this way and that. Well, the width will absolutely gobble stuff up here and there in nuclear geometry and play a large role in determining the final breakup channels. With CO2, we've been doing calculations to try to make sense of everything. Right here, you want to look at that conical intersection with the arrow. We have the double pi G Feshbach resonance labeled there on the left, and the pi U shape resonance also labeled on the left, and they intersect there around 5 eV, 3 point something Bohr. Now, we think, dissociative electron attachment occurs via both these states, pi U and pi G, okay? Despite the fact that you can see right there's a barrier formed by that conical intersection. So the idea is that what must be happening is that the molecule must circumnavigate that conical intersection in order to dissociate. So that's borne out by angular distributions that have been measured. They're very smeared out. We published a couple of papers on that. So that, in order to calculate that precisely, you have to do polyatomic quantum nuclear dynamics to actually get like a result for the cross-section. And in order to really just start from theory and really make a quantitative prediction about exactly what angle, exactly where does that conical intersection happen, we have to go to very high levels of theory. I've just put some potential energy curves here that have been calculated with Columbus quantum chemistry program. It's like 40 million configurations. With 40 million configurations, I can get all the energies of the relevant states rather quantitative. And the circle is trying to follow the conical intersection. It drops below the initial energy and then disappears by 120. So these calculations indicate it's about a bond angle of 140 degrees that the molecule should dissociate at.
Don, when you say 40 million configurations, does that mean electronic states or?
It means spin adapted configurations in the CI. Yeah.
So CI expansion of all the electronic states of the CO2 molecule?
It's a CI expansion, and we diagonalize it to get the states. Yeah. Maybe just come back to CO to NO2. H2O is a little bit more interesting for the moment. We spent a lot of time studying dissociative electron attachment to water. You already saw a couple figures here. Here's just another couple figures showing the 3 electronic states using O- and H-. So we have 3 electronic states, several breakup channels. Our investigation has been years long and has been all about the polyatomic nuclear dynamics. We've calculated some cross sections, but a lot of it has been trying to describe the dynamics of dissociation. So we've come to some conclusions. Those conclusions are here. They're not really apropos to uncertainty. So in order to do a complete treatment like we've done with water, we do it with 2 steps. Well, there are 2 main components of it. We have to first define our complex potential energy surface, and then we have to calculate dynamics on it. So operationally speaking, how we do that is we use scattering calculations to produce a width. We use large-scale CI calculations in order to produce the real part of the energy. Now, when we do that, we have a big trade-off, because if we just use regular bound state quantum chemistry, we're going to make a significant error. That error is going to be on the magnitude of the width. We're approximating the bound state as the resonance state as a bound state, just to get the real part. So right there, we're making an error of plus or minus the width into the location of that resonance. We could use the complex cone to calculate both E sub r and gamma, the position and width. But because of the lower level of electronic structure in the complex cone, the results aren't as accurate. So, and so once we've calculated those quantities, we can fit a potential energy surface and run, I've just written down the potential energy, complex potential energy surface there. We use the multi-configuration time-dependent Hartree-Fock method for that, and I'll talk a little more about that later. Here's a picture of some potential energy surfaces just showing you the situation for H2O. You see if you start on that upper state B2, you can be funneled into a conical intersection. And all this talk about complex potentials, you know, the whole picture that I've drawn with potential energy curves going above the neutral, and you know, I kind of fuzzed them out to indicate they're complex. That comes from, that's the local complex potential model, and it's an approximation. In general, it's sufficient for dissociative electron attachment. The derivation isn't too important, but we talk about projection operators. We can, if we have an approximation to the resonance phi sub alpha, we basically formulate the effective Hamiltonian within that Hilbert space. This is getting a little too detailed. The point is, we have a complicated formal, a nasty formal expression there for the effective Hamiltonian that math is done on, and to arrive at the approximation that that whole thing is just a local absorptive part due to the width. Now, it's important to mention that there are many systems for which the local complex potential model doesn't work, including those that have been studied by folks in the room, including Carl Hufek. And I just put up a recent reference if you're curious about that. Okay, so we go through, we construct a potential energy surface that's good out to dissociation. There are various cuts of it, showing a couple breakup channels labeled with arrows. And we calculate the dynamics again with with MCTDH method. This is an adaptive method capable of handling systems far bigger than a triatomic. They've done calculations on vibrational dynamics of things with 24 atoms or even more, I think 45. The issue with doing a calculation with MCTDH accurately is not in MCTDH, it's in the potential surface. So the method is highly adaptable to polyatomic dynamics. And putting that all together, we can calculate the cross-section. This is a zoom up of that biggest peak that you saw on a previous slide. This is the total DEA cross-section producing H minus. That's the total is the one on top, bold black. And then broken down into the final vibrational states of OH that are produced. So you can see with this system, which is, as far as a polyatomic system that undergoes DEA, you probably can't get much simpler than H2O, as long as we define poly as 3 or more. So this shows that in a relatively easy case, we can calculate polyatomic dynamics and produce cross-sections that are close, 10%. Here I've just put up the numbers. I'm going to show some more results, but what I basically want to point your eye to is the survival probability. These are again for these 3 states in H2O, low to high, B1, A1, B2. I just want to point out that the survival probability for B2 is relatively low, so we'd expect that it'd be harder to calculate the B2. So here are the results for the second peak. You saw the first peak. The second peak here is for H minus. That's this guy, so it's on the shoulder of the B1 peak. So there's some overlapping here. I calculate 5 or I calculate 0.5, and right here it's 1. So we've definitely gotten in the ballpark, and it's hard to tell from the experiment whether or not we're completely accurate. So then here's production of O minus. You can see that there are the 3 peaks. The first peak, we didn't get any. Okay, so attachment to the lowest energy resonance, well, we got about I think I said 1/100th. It's either 1/100th or 1/1000th, the actual result. So we checked the hypothesis that this is due to Renner-Teller coupling to the other surface. That wasn't the case. In the end, I suspect that it's due to deficiencies in the surface. On this particular state, the B1 is a very flat region of the potential energy surface, and we didn't try to play around with it, but I suspect if you just move that, you just adjusted that big flat plateau a little bit, you'd get some of the wave function going into the well describing O minus plus H2. So that's the number one hypothesis, that it's just a potential energy surface issue. We're very happy with agreement for that second peak. Couldn't have expected to do any better than that for sure. And the third peak, that is fortuitous. We cannot guarantee that level of accuracy in general. Okay, so yeah, that's good. I can talk about NO2, but I'll conclude. So I'll just reiterate. We have vibrational excitation, we have dissociative electron attachment, they compete. It's hard to calculate a minor channel. If DEA is the minor channel, good luck. So that's it.
Again, coming back to yesterday's discussion, are these experimental data that you compare with, are they absolute, or how have they been measured?
No.
How reliable is the whole cross-normalization thing?
Oh, I couldn't speak to the cross-normalization, and I don't think there's any absolute normalization, but I'm not completely positive. I couldn't tell you how they do their cross-normalization. I think O2 is a major one that they calibrate.
You believe it, let's say. So you see, in many cases, say, people who want to apply these cross-sections, they need absolute numbers.
Uh-huh.
So my question is basically, if you look at the shape or whatever, is there any indication about how good your theory is compared to really true absolute experimental numbers, or are there reliable experimental numbers available, for example, things like that?
The most recent data on H2O that's quantitative was what I plotted. I can get you that reference. It's Fedor et al. That's the most recent absolute measurement.
And your theory is, did I get that? Maybe I missed it, but your theory is also absolute?
Yes. Yeah, those are absolute. Yeah. Mm-hmm. Yeah.
But you wouldn't know an error estimate on the experimental absolute number.
I'd have to consult the paper. I can say, so we work both with Ali and with Alan Landers, my photo at Auburn, and they do the velocity slice imaging method as opposed to the Coltrane's method, and they have different uncertainties as a function of the fragment energy. So if you look at, if they got their electron gun at a certain energy and they're measuring the kinetic energy distribution of what comes out, have seen big differences between those two data sets. So I think that's all I can tell you. I think that's all I can say.
I have a query about your methodology, because normally the width is much more sensitive to the level of wave function you use in the position. So widths move around all over the place as you change the wave functions. Normally the positions are reasonably stable.
But
you're using a method where you really
on a relative basis,
by doing a very large.
You're talking on a relative basis. The width is very small, so proportionally it changes by a lot.
On a relative basis. There's
On a relative,
percentage change in the width. You know, you can change the width by a factor of 2 fairly easily by changing your wave function. And I've been there and done that, so I really can.
If you try, you can do it. Yeah. Depends.
You don't have to try that hard.
Well, you can just do a Hartree. You could, you could try. Yeah, you don't have to try very hard. I could change the charges on my nuclei, or something really stupid.
With reasonable terrestrial models, the width is normally not that stable. Yet you're using much smaller models to do your width than you are to do the position.
Okay.
I understand you.
Well, I was talking about the work on H2O, which is the only time we've actually ever done calculations with the surface. It would be an overstatement to say we have a general methodology. Right now our methodology is put stuff in the apparatus and measure the angular distributions and calculate the attachment probability and try to figure something out about the dynamics. We don't currently have any interest in doing polyatomic calculations on a full dimensional potential energy surface because that takes 5 years. So we are very much looking at trying to what we are doing right now is really going for more qualitative things. We are not going to attempt, I don't believe, to calculate CO2 cross-section. So.
That's the problem I also set that from, so I don't blame you.
Then you're happy to explore the static in regions where you have electronic excitation.
Explore the.
The static that you're using for association in regions where you have electronic excitation channels open.
Oh yeah, I'm glad I kept that slide. Some of these studies involve. Tell me if I'm not answering your question. Some of these states are very high in energy, so they do lie above many excited states of the neutral. So these are all a plot of all the target states that go into the Cron calculation. That's the lines with dots. And the fitted positions of the resonances are the solid lines. So, so here, I mean, we have at the most. This is not the worst case scenario. I think at the most, I had like 20-some channels open, like the last 5 or 6 of which were probably nonsense, but just in there to converge. You have to accurately represent manifold of states here up fairly high. That doublet B2 state. This this guy can get really very high in energy and in fact can go above the ionization limit. So actually, hypothetically the highest energy state could decay by emitting 2 electrons, actually. So that's how high energy it is. And this makes it harder with the electronic structure.
You complicated you thought water was the simplest triatomic problem. I disagree with you exactly because of this plot.
Oh, okay.
There are probably
H3
there are probably molecules which have resonances which are separated from. I don't not sitting here with an example. But for diatomics, in one cases, the resonances are well below electronic excitation. So it must be true for triatomics as well. And you've got 3 resonances,
Right.
and you've got all this mixture of
Certainly.
electronic states. So this is not a simple problem.
Well, the B1 is pretty simple.
Yeah, okay.
This guy is pretty simple.
Okay.
Yeah. I mean, he really never crosses his parent. He's always,
Yeah, okay, so
He's
the last one
always
is, simple.
yeah, yeah.
And the others are less.
That's the one where you could like actually really do a quantitative calculation and have confidence. You know.
Yep.
I want to pick up on something that actually you said yesterday
Yeah.
in some stage, and that is, and it also came up a little bit in the electromagnetic and even the two-particle models. Could you make an uncertainty estimate on your results if you didn't have experience?
On like a results for a full comprehensive wave packet propagation.
I mean, any of the results that you presented.
Well, let's.
If you didn't have experience, could you? I mean, I
Sure.
don't know much about this field, right? So I just
Yeah.
want to know, could you make an estimate if you didn't have?
He actually gave us the sort of, he said the inverse survival probability.
Yeah.
This is uncertain,
Well, I mean-
probably speaking.
Yeah.
Oh,
There's a
yes,
units
that's
problem
right.
there. I haven't got quite the right units,
No.
but it's proportional to the inverse survival
Right. Yeah.
probability, which is a purely theoretical number. So you believe the things with a large survival problem.
I would disbelieve things with the low survival.
Yeah, okay, all right, fine.
Yes.
But that's at least a rule of thumb for.
Yeah. But I mean, otherwise, I mean, we certainly don't have any rigorous way of doing so, and I would assume it would take something like. We don't have a good way.
Well, since you can-
just a qualitative question.
You
Yeah.
can, I mean, your MCGH calculation is relatively straightforward.
Yes.
So it's not impossible simply to move the curves around.
Oh, yeah, it's quite easy.
There's
Yeah,
some limits.
absolutely.
Repeat the calculations.
absolutely.
You know.
Right.
Uh,
Yeah, sure. Well, certainly, yeah. Given a model, absolutely. I mean, always if we're doing statistics, we have a model. If we have some model and some parameters of that model, we can always do statistics on those parameters. So if I start, whatever I'm doing, if I'm starting, let's say I'm considering the angular distributions and due to the symmetry of the molecule, the transition moment has to have a certain form, and that's my model. And I take my experiment and I can, I'm glad I took intro to statistics a while ago, because there are just some various. As long as you have a model, you can model that's parameterized. You can do some statistics and produce some uncertainties with the general framework that we assume the model is correct. That's my understanding of statistics. We say, okay, I have a model. We're assuming it's dissociating on a local complex potential curve. We have to assume the DA model applies. If the DA model applies, then if this model is correct, then what is the error in the experiment given the model? That's the general framework that I learned back in college, but haven't had a chance to apply yet.